All right, chapter 15 is on acids and bases. We're going to be using a lot of the concepts that we learned in chapter 14 about equilibrium later in this chapter to talk about acids and bases. First, we need to define acid and base. An acid has three different common definitions. The simplest is the Arrhenius definition, which focuses on the fact that acids make H plus in solution, bases make OH minus. The Bronsted-Lowry definition is what we are going to mainly use in this chapter. It focuses on the proton, H plus. Acids donate an H plus, bases can accept an H plus. This is a broader definition than the Arrhenius, but it includes all Arrhenius acids and bases. And then Lewis acids and bases focus on electron pairs. We'll talk about that at the very end of the chapter. For now, we're going to focus on the Bronsted-Lowry definition of acids and bases. There are several structures of bases. Binary acids, we've talked about before. They have an acidic hydrogen attached to a nonmetal. So, for example, hydrochloric acid or hydrofluoric acid. And they are very straightforward. There are things called oxyacids, which have an acidic hydrogen attached to an oxygen atom. Examples include sulfuric acid, H2SO4, and nitric acid, HNO3. You can identify acids in this course by the fact that there is an H out front in a molecule. So the H2, both of those H's are acidic. HNO3 has one acidic hydrogen. That comes in handy when we're talking about carboxylic acids. Carboxylic acids have this COOH group, so a carbon double bonded to an oxygen and then another oxygen with a hydrogen. That hydrogen is acidic, but other hydrogens in organic molecules are not necessarily acidic. And so the first H in the formula is acidic. If there are other H's around, they are not acidic. So for example, acetic acid is HC2H3O2. That first H is acidic, the other ones are not. And then citric acid is the other example there, has 3 acidic hydrogens and 5 that are not acidic. Those kinds of acids occur in a lot of different natural products, fruits, that sort of thing. Citric acid, malic acid is in grapes and apples, acetic acid is vinegar, that sort of thing. Okay, let's dig a little bit more into Arrhenius theory. It says that bases dissociate in water to produce hydroxide ions and cations. So bases in Arrhenius theory are things that directly produce OH minus. And then acids ionize in water to produce H plus ions. Molecular acids aren't made up of ions, and so they can't dissociate. We use the word ionize. They're pulled apart by the water. And like we said, the ionizable H or the acidic H is written in the front. Now, we'll just jump right into the problems with Arrhenius theory. It's not broad enough for our purposes. It doesn't explain why some molecular substances, like ammonia, will dissolve in water and form basic solutions, even though there's not an obvious OH minus in there. And it doesn't explain how some ionic compounds that don't contain a hydroxide, like sodium carbonate or sodium oxide, will form basic solutions without that. And it also doesn't explain why some molecular substances, like carbon dioxide, will dissolve in water to form acidic solutions, even though there isn't an H plus around. And you're also stuck in aqueous solution for Arrhenius. So we're going to use Bronsted-Lowry, like I mentioned, and they redefined acid and base based on what happens in a reaction. So any reaction that involves an H plus being transferred from one molecule to another is an acid-base reaction. It doesn't matter if it occurs in aqueous solution or if there's hydroxide present. And another useful thing is that any acid that fits the Arrhenius definition is also going to fit the Bronsted-Lowry, but it's going to be much broader as well. So an acid is going to donate an H in an acid-base reaction. The base is going to accept it. And because the base is accepting the proton or the H+, I'm going to use proton, H+, and H3O+, pretty interchangeably in this chapter. They're all essentially the same thing, the acid part of the reaction. And the acid's going to give that H+ to the base, which can accept it then on its available electrons. Now, some materials are amphoteric. An amphoteric material, substance, can act either as an acid or a base, depending on the situation. They're going to have both a transferable H and an atom with lone pair electrons. For example, water can act as a base, accepting the H+ from hydrochloric acid. And so get hydrochloric acid plus water gives the chloride ion, plus there's H3O+, that is the hydronium ion. But water can also act as an acid, donating its H+ to ammonia. So in this case, ammonia plus water gives us the ammonium ion plus hydroxide. And so when you write out the whole reaction, you can see why ammonia is basic. You're creating this hydroxide in solution. An advantage to Bronsted-Lowry theory is that it allows the reactions to be reversible. So you have an acid plus a base gives us a new base and a new acid. The original base now has the extra H+, so it can act as an acid. The original acid now has a lone pair, so it can act as a base in the reverse reaction. Now those, you can see it kind of forms pairs. Those are called conjugate pairs. So anytime you can remove an H+ or add an H+, you're going to get a acid conjugate base in the case of removing H+, or a base conjugate acid pair. So your acid, when you remove the H+, becomes its conjugate base. A base, when you add an H+, becomes its conjugate acid. So we can work through understanding getting a conjugate acid from a base. So if we're writing conjugate acids, that means we're starting with bases. So H2O, it's conjugate acid. We've added the H+, so it's going to become H3O+. Ammonia, if we add an H to it, becomes an H4+. CO3 2- becomes H. CO, that's an H, not a 4. CO3-. Remember that H is coming with a positive charge, so make sure you account for that. And H2PO4 -1 is going to become H3PO4 neutral. What about the conjugate base? So for writing our conjugate base, we're going to get rid of an acidic hydrogen. So here our water becomes OH-. Our NH3 would become NH2-, which does exist. CO3 2-, there's nothing weak, there's no hydrogen to pull away, so there is not a conjugate base for the carbonate ion. And H2PO4 can become HPO4 2-. Okay. Write the equation for the following reacting with water and acting as a monoprotic acid, and label the conjugate acid and base. So HBr plus H2O. Write our equilibrium arrows. In this case, it's pretty much just that way. Goes to H3O plus Br-. We have our acid, our base, which means that our H3O plus is the conjugate acid and the Br minus is the conjugate base. So your acid always becomes the conjugate base, your base becomes the conjugate acid. And then H2SO4 plus water reacts to form H3O plus SO4 2 minus. And again, our water, or our H3O plus is our conjugate acid, and our sulfate is our conjugate base. All right, strong acids. The stronger the acid is, the more willing it is to donate the H. And so strong acids donate essentially all of their hydrogens when in water. You can think of them as being 100% ionized. They are strong electrolytes. And the H3O plus concentration in water for them is the same as the concentration of the strong acid. So if we do hydrochloric acid, 0.1 molar hydrochloric acid gives us 0.1 molar H3O plus in solution. Weak acids are only partially ionized. Just a fraction of them donate the H. Most of them do not. Here's where we really use the equilibrium arrows. And then our concentration of our H3O plus is going to be far less than that of the weak acid. We're going to have to use equilibrium calculations to figure out our concentration of our H plus. Here's a table that can be useful to reference. Notice all of our binary acids, starting with hydrochloric to hydroiodic, are strong. Hydrofluoric, however, is weak. My line between strong and weak is right about here. So anything that's a weaker acid than water is going to be considered weak. And then up here is strong. And then down here, anything down here is going to be a strong base. And then up farther are weaker bases. So general trends, the stronger an acid is at donating the H, the weaker the conjugate base is at accepting it. So a strong acid is going to have a very weak conjugate base, whereas a weak acid, its conjugate base is going to be a weak base. The higher the oxidation number, the stronger the oxyacid. So sulfuric acid is stronger than sulfurous acid. Nitric acid is stronger than nitrous acid. And anything that's a cation is going to be a stronger acid than the neutral molecule. Neutral is a stronger acid than the anion.